give us a talk today on finite groups yesterday and today.
Thank you. Well, I'm glad to be here, and thanks for the very nice invitation. I chose as topic the history of finite group theory because I find that this has a curious development which is not so common in mathematics. So let me start a little with the old things. We could start with Galois, but I don't want to spend too much time on that. Around 1930, just to say that he already had some precise knowledge of simple groups. He knew the alternating groups, but he knew also very well PSL2 P. And he knew it really. I mean, there is in his letter to Chevalier before dying, the day before he died, he said that this group acts obviously on P+1 objects, the projective line, and Galois said it acts also transitively on P objects when P equals this and nothing else. So that meant that he really had a good knowledge. So in the 18th century, what I want to point out are just basic theorems were found, like Silo and Jordan-Holder. Classical simple groups were found essentially by Jordan. And sporadic groups, they were not called sporadic at the time, but they are sporadic groups of Mathieu, 5 of them. Around 1960, I don't remember, 1862 or 61, I think, and 1873, something like that. The big Mathieu then and the small Mathieu's here. Okay. The interesting things started, or more interesting, started around in that period with Frobenius making up a theory of characters, and later noticing that the characters are related to linear representations, because his point of view was not to start from linear representations as we did. He was starting from the determinant. He was factoring the determinant. And Frobenius and very soon Burnside took up Frobenius theory. And the two of them had a little competition, clearly. I mean, they were proving theorems and the second one making it better. But at the very end, very nice. Each of them found an excellent theorem. Burnside found the theorem that if a group has order, traditionally it's written P, A, Q, B, P and Q are primes, A and B are integers, so just 2 primes, then that is solvable. And the proof by character theory is by far the best of the known proofs. There is another one. Frobenius found something which turned out to be equally interesting. It is the following. Suppose you have a group G, finite, and you have a subgroup H, and suppose that, as people say, H does not intersect its conjugates, which is a bit disgusting way of saying that H intersected GH, G minus 1 is 1 if G not in H. But Frobenius would rather see it in the following way, that you have G acting on a finite set X transitively. And then the condition here means that if G in G fixes 2 points, 2 distinct points, then G is equal to 1. You see that that is the same, because if fixing a point means being in H, fixing another point means being in one of those, and that's forbidden. And then he proves a very strange theorem. I don't remember the date, but I think it is around 1902. That if you take the elements which fix nothing, the set n of G in G fixing no element, and if you add to it the element 1, then this is a subgroup. It's very rare that one construct a subgroup in such a way that it is not obvious that the product of two elements is in it. So the difficulty is to prove it's a subgroup. Of course, when you know that, it is a normal subgroup, automatically, by definition. And also, it's also obvious that the group G is a semi-direct product of H and N. And you have to think as the prototype of this is a group of transformation X goes to AX plus B. So on the line, taking A and B in a field, finite field, and A invertible. Then the H fixes a point, so it is X goes to AX, that is H, and the N is a translation. So that's the usual decomposition of an element as homothéty and translation. And in a sense, Frobenius theorem tells you that that's all there is. And the only proof known even now is by character theory. And it is a splendid proof, because the idea of the proof is the following. You want to prove this N is a subgroup. So what you do is you make up a homomorphism into some GLN, and you make it such that the kernel is N. And how do you do that? Then, of course, it will be a subgroup. How do you do that? Well, you say, I'm constructing the character of the thing. You cannot construct the representation, but you construct the character. The character is a class function. It's easier to write. You write it explicitly. You start with the representation of H into some GLN. It has a character. You extend it to G by some formula, and you win. The interest of this is also that the theorem of Frobenius gave rise to two different equations, and both of them very interesting. When you have such a situation, G equals Hn, like in Frobenius, and non-trivial. I mean that G is not 1, H is not 1, and is not G. Non-trivial thing like that. Then N is called, for obvious reasons, the Frobenius kernel. And H, which is not unique, you can conjugate H, but that one is unique. The Frobenius complement. And the question of the structure of those things turned out to be important. The Frobenius kernel in particular. Because in the example I told you, Frobenius kernel is just translations by B. It's commutative. And if you make up examples, you see that you easily make them with N commutative, but it's pretty hard to make them with something else. What is the condition for an N to be a Frobenius kernel? It's equivalent to the following. There exists an automorphism sigma of n, such that there is no fixed point except just one, and sigma as prime order. A proof, you take in H an element of prime order, and its action of n is like that. And so the question became pretty soon known as the following question: prove that such an n is, in fact, the best answer is nilpotent. It's not abelian, but it's nilpotent, and one knows, I'm not sure one knows exactly, the nilpotence exponent depends on the prime. If the prime is 2, for instance, it's trivial that the group is abelian. If the prime is 3, it's non-trivial, but not very hard, the nilpotence class is 2. If the prime is 5, I think the nilpotence class is 6. After that, I think one doesn't know exactly. But that was a very important question. I will go back to it later. I want to say something on the complement. The Frobenius complement has another characterization. In the differential topology, people are interested in classifying Riemannian manifolds with some properties. And in particular, they are interested in classifying compact Riemannian manifolds with positive curvature. And even better, constant positive curvature. And the model of that is a sphere, of course. The sphere Sn is like that. And what these people can prove is that if you have such a manifold, its universal covering is going to be a sphere. So such a manifold will be the sphere divided by some finite group H, acting on the sphere by rotations, and freely, because it has to be a quotient, a honest covering. But that is almost, you see, like a Frobenius complement, because it means that H acts on the linear space here freely outside 0. Of course, it's not finite, but standard arguments, whenever you have a representation in characteristic 0, you can reduce it mod p for some p, and you still get something with a free action outside 0. So that is the characterization. And so the only book where one finds a complete classification of H is a book on Riemannian manifolds. But I want to go back to this, because that was one of the main questions for a long time, and it was quite a success when Thomson, in his thesis, proved it. Not a long paper, no, I mean, with respect to group theory, it's not a long, short.
He proved the nilpotence of n?
Yes.
Okay.
As a matter of fact, he proved that it is solvable, but it was already known that solvable implies nilpotent. Okay. It was a paper about 20 pages and a pretty difficult paper. It was slightly before 1960. Well, I'm not sure. 60 minus epsilon. And a few years later, he found a proof which he published in about 4 pages. In 1963 or 4, something like that. And the story is that he was rather disappointed that he could make his thesis instead. But I've tried to read the pages, and I gave up after. Well, they are very concentrated. But in that page he introduced quite new methods, new functors, because finite groups, curiously, has functors and things, but they are very limited. I mean, they. For instance, here he would take, I think, a P group, and would take the subgroup of it generated by the elementary abelian subgroups, something like that. It is a functor, all right, but not of the type used elsewhere. So I think that was, in between, what things interesting between 1900 and 1960. One thing is the definition of the transfer. That was in a paper of Schur, but he did not give it a name, and he used it just to reprove a known theorem. He did not make any impression on the mathematical public. But it was Artin, around 1923, who saw its use in class field theory, and then it became an interesting object, which has consequences for the structure of groups. But as a matter of fact, most of the consequences of the transfer were already known to Frobenius and followers, because the transfer is almost the same as the following. I mean, the co-restriction of a homomorphism is almost this. You induce the representation. You get a representation of larger dimension, and you take its determinant up to some sign. That is a transfer, essentially. So they had a tool equivalent to the transfer. So the transfer did not prove much theorems on finite groups. It's still useful, but there was at least one theorem which was a bit surprising. The transfer in general is the following. You have H in G of finite index, and then the transfer goes in the non-obvious direction. G made abelian into Verlagerung H abelian. And the curious theorem, which Artin pointed out, he could not prove it, but he stated it, the theorem, if H is the derived group of G, then the transfer is 0. Is trivial. In class field theory, it is a fact that if you have an ideal in a ground field and you go to the Hilbert class field, it becomes a principal ideal, because being principal means getting 0 in a class group, and that is what the transfer gives you. Okay, so I am arriving in the 60s, which is a very interesting period. Up to that point, there had been nothing much, except I forgot to say still something important. In that period, starting even around 1935, Richard Brouwer investigating representations in characteristic P. And quite soon he obtained results which had consequence on the structure of the groups. And also consequence in characteristic 0. He proved he solved the problem of Artin, of showing that any character is a linear combination of induced characters of degree 1. And his proof was inspired by what he had done in characteristic P. Even so, it is a theorem in characteristic 0. So that was really important. But except for that, what was known on finite groups could be found in a small book. I remember when I was a student reading Zassenhaus, Group and Theory. It was not translated in English. I had it in German. And in the little book of about 200 pages or less, that was essentially everything except for Brouwer known on finite groups at the time. It's not the situation now. In the 60s, things started exploding because there was also around 1968, I guarantee you the date, there was Finite-Thompson. Groups of odd orders are solvable. Or, if you prefer, no simple group of odd order except the cyclic ones. Thompson explained that the idea of the starting point of the proof was by some older result of Suzuki around 1950, if I remember correctly, something like that. Suzuki proved this for groups of odd order with a very strict condition on them. He proved it under the condition that if x is in G, x not 1 implies the centralizer of x is abelian. Well, for very small groups like PSL2, I mean, you have that property, but not many others really. A bit later, in between the two, Thomson, the other, replaced abelian by nilpotent. But that is not a very big improvement. The proof of that was rather sensational, if only because of its length. The proof was taking up an entire issue of the Pacific Journal of Mathematics. So the paper has, I don't remember, I think it's about 250 pages. You will see more later, but for the time, it was a kind of record. Maybe it was a record for the length of a paper. And it was not easy reading because there are long papers that, for instance, when Hirona-Cap did the resolution of singularities, it was long, but people said that it could really check rather easily step by step. These steps were much more delicate. I should say something about that. A proof by contradiction, because it's a proof by contradiction, you have to show the thing, is dangerous. Because if you make a mistake, it helps you. Because you make a mistake, and you go on, and then something wrong happens, and you say, I have won. It's very different from when you prove something positive, like you construct an object, like finality construction. So any stupid mistake helps. And in fact, Fate and Thomson told me that that is what happened to them. That is, they had a manuscript ready, and then one of the two, I think it was Fate, found that some stupid elementary inequality between integers that they were using was just wrong. And they could not repair it immediately. they had to write an entire new chapter with completely different ideas to overcome that stupid thing. To reassure you, recently some people did something very remarkable. They have a system of logic. Well, I don't know how to call that. I mean, they wrote the proof in a completely computerized language, so that one can be sure, assuming the language is okay, of course, but one can be sure that the proof is correct. Which means that in such a proof there are always little misprints, even maybe some mistake for a simple lemma. And so they had to ask somebody to check those things. I mean, the machine could not do that. But after it was done, they have a complete proof. So that was a problem which Burnside had pointed out, because all the groups that were simple groups known are obviously order divisible by 2. What is curious is that nobody asked groups of order divisible by 3. In fact, Thomson spoke in Paris once on the odd order, and somebody in the audience told him, did you try to prove that there is no simple group of order divisible by, not divisible by 3? He was a bit mad at the question. Well, it was the case they didn't try, because counterexamples were found by the Suzuki groups. We were found in the 60s. Have order non-divisible by 3, and according to the classification, they are the only ones. So the Suzuki are like that. Not, if I may say so, divisible by 3. But that really came as a big surprise. So how do I continue? How does the story continue? Of course, the story continues by the classification. The first ideas about the classification are, I think, the beginning of the 1970s. Around 72, I think, the announcement by Gorenstein. Gorenstein had the vision to construct a scheme of classification of finite simple groups in a rather complicated scheme, because he published, in fact, books. I don't remember whether it's 1 book or 2 books, just describing the steps. You see, not doing them, describing them. He published that, and giving a complete classification. And as you know, the complete classification is that you have all the groups like Chevalet, Suzuki, AN, more or less classical groups with some variation, and 26 others. But the 26 others, they were Mathieu, of course, 5 of them, but the rest, Yanko 1 was found in 1966, and the last one is Yanko 4, 1976. So in this 11 years span, 21 groups were found, so roughly 2 a year, and we were getting used to that. You see, we were asking, what are the new simple groups found? And then the thing stopped. And Gorenstein announced the classification even before the last one were found. But he said, well, should work. He came here. I mean, he came by that door and he went to here. And that was around 1972 or 3 probably. And he gave a lecture on his scheme of classification. And it made a big impression on gross. Oh, you think it's 74?
This room was over here.
Oh, yes. Yeah. It made a big impression on Gross and me, because Brouwer was seated either where you are or where Gross is. And at the end of the lecture, he went to the blackboard. He was clearly not in a happy mood at all, curiously. And he said, I'm going to tell you a little poem, which I think he translated from the German. And the poem was about a mathematician. And the mathematician saying, oh, I'm going to be world famous. I have proved Fermat's theorem. All I need is a little lemma. And then he went back to his seat. Well, Barry, you were there, but it did not impress you. I mean, myself, and I was very surprised. Brouwer was usually an extremely gentle person.
Very gentle.
Very gentle. So that meant that announcing without a complete proof something which for him was really the holy grail, you see, I mean, the classification of finite simple groups, daring to do that, he resented it. Story seems to show that he was wrong. Now, the classification, assuming it's true, or maybe I have already said too much, I should explain. The fact is that Gorenstein gave the program in 72, I think, and in 80-something he said it's done. And he was jumping the gun, because it was known, probably to him also, that a part of the proof, I don't know what those groups are, I just know their name, quasi-thin groups, had not been really classified. When I learned about that, I asked the specialist, I mean, what is the situation? They all said, no, don't worry, there is a manuscript. But there are pages missing in the manuscript. It's not even numbered, the pages are not even numbered, and the guy who wrote it has given up also, but except for that, we are sure it's not serious. So I was about mad about that. Later, and then I'm jumping a little later, quite later, Aschbacher and Smith published 2 books, 2 volumes, for the little gap which did not exist on the quasi-thin. Yes. So I was at least happy to see that it was not a trivial gap. It was, but they refused to call it a gap. I don't know. I told them if, for Fermat, for instance, somebody had said, oh yes, we have a proof, but there are a manuscript of 200 pages with pages missing, and so everybody would have laughed. But no, the finite groups people accepted that. But they were confident that it was a matter of time, of work. So at the moment, there is no official gap. There is no complete proof either, in the sense that there is no place where you could see a linearly ordered succession of theorems, at the end of which you find the proof. No, the linearly ordered proof is being constructed for 20 years. People have been working, and they have published, I think, 6 or 5 books, and they are in the middle. So in 10 or 20 years, probably we should see the these are beautiful consequences, which I will state in a moment. But I would like to say also that when people invoke the classification, they use two things. First, that no other simple group that is really the classification than the list, and two, the properties of the sporadic groups. And quite often, the property of sporadic groups including the table of characters. In the atlas, and this is why I took this. For instance, if you take the monster, and I'm not going to read you the table of characters of the monster, but there are 8 pages, printed very small, but not much. If you think that the monster has about 10 to the 54, I think, elements, but it has only exactly 140 conjugacy classes. So that you have a table 198 by 194 by 194 with big numbers, but not so enormous, really, much less than the order. The only trouble is that the atlas has no proof. And the atlas is just an atlas in geography. The atlas in geography, nobody proves to you that the country exists, you see, with this river and this and so on. I mean, this is just... there is no doubt that they prove things, but they never publish, not even a sketch of the method. I think one should force them one day by some open letter or something to give at least some information how they did it. Because when you take a group like the monster, they did not know in advance that there were 194 classes. They must have determined the classes at the same time as they made the characters. And absolutely no proof. In the introduction, they say that they have checked orthogonality conditions and so on, but also they are very honest and they say that just before giving it to the printer, they found that a bunch of characters for some group was wrong, so they replace it. They replace it by another one. And unfortunately, those are useful. For instance, so let G be simple, finite, non-abelian. And I take Z in G, then G is a commutator. Impressive. Fortunately, you don't have to look at all the elements of the group to see that. There is a formula which tells you the number of ways. So the number of ways Z is a commutator, that is the number of pairs x, y, such that x, y, x is Z. This number is equal to the order of G, sum over all the character chi of chi of Z over chi of 1, chi irreducible. So you see, for the monster, there is no problem because the character table is on the computer of somebody. Certainly Conway has it. So you can program very easily to take every one of those class compute this sum. It's a small sum for a computer, 194 elements. I mean, it's nothing. And then you find that it's non-zero. And so that is the way the theorem was proved for the sporadic groups. Curiously, it was not easy to do it for the Chevalier groups. The Chevalier groups overfilled with small number of elements turned out to be very hard, even using that formula. Because one needs to know the characters in detail. For instance, if you think of it, of that group, which is even bigger than the monster, like quite, even for that group, you need to know the characters of E8, and there is only practically one person who knows that, it's Lustig. So,
is that how this group was found?
it is indeed a question of bound, because in this formula, the character which is important is the character 1. See, it gives you 1 here. The others, they are, for a large group like that, they have a very large degree. And usually they are much smaller for the elements which are not 1 than for 1. You see, and so you want to do the proof mostly by proving that those things are so small that even their sum does not compensate 1. But you need to have a really good knowledge on the characters.
No, what I was trying to ask you is that how the TITS group was found, right?
How the
group of TITS, which isn't actually on either one of your lists. It's neither.
Well, it is a small change. But one has the character table also, but I don't know how they got it.
Because, I mean, you could, it's 2F42 doesn't actually satisfy this result, and that's because it has a subgroup of index 2.
No, I don't understand what.
He says the TITS group is the commutator subgroup of index 2 of twisted Chevalier group.
Yes, but that doesn't change anything in the formula. I mean, there is no element of order 2, no central element of order 2 in the TITS group. It has disappeared.
No, but I mean, the Chevalier group doesn't have elements that are not commutators. And I was asking whether this kind of formula was how that was noticed.
What do you mean? The theorem says that they are commutators.
In the TITS group, but he means in the larger Chevalier group, of which the TITS group is the commutator subgroup. Is that how the TITS group is?
That I don't know. I don't know in the TITS group really. It's not clear. I mean, the -1 in the kernel might be a commutator for all I know. Probably it is. I would assume. I don't know that. Oh, but the quotient of order 2. No, of course not. There's a quotient order 2, so commutators are just the TITS. Okay, now I will finish by just showing you, because I have nothing to offer to you, so to in front of this situation. We have a kind of gray case where proofs depend on things which are printed, but printed with no proof. And it is not reasonable to believe that a complete proof could be given for the character tables. I mean, that would be, even for smaller groups, it's pretty difficult to do. Frobenius computed in his work the character table for Mathieu 24 with some details on the proof. Okay, I want to show you one application and also one which at the time made me rather mad. But not anymore. Well, it's more than 20 years ago, so I think I've got over it. But it is such a beautiful statement. So theorem, modulo classification plus epsilon. Finite group G. It acts on X finite transitively number of elements of X at least 2. then the theorem is there exists an element G in G of order a power of a prime which has no fixed point. If you don't put that, that is a very easy exercise. It was known to Jordan, it's very easy. The main thing is that another way to see it is, it is essentially the same. When you have a group, when you have G not 1 in G, or no, one or not, when you have G in G, you can look at the orbits of the cyclic group in X. So you get orbits. And you can look at the greatest common divisor, GCD, of the orders of orbits. And then this thing is equivalent to saying that there exists G in G such that the GCD of order of orbits is than 1. If you accept that, if G has order power of prime and fixes nothing, all the orbits are order power of P, non-trivial, and you have that. And the converse is you take the P part of such a G. Okay, and this, in number theory, if you use Chebotarev, can be translated the following way. Finite extension of number fields. Of degree at least 2. Non-trivial. Then there are, well, there is a P, a prime P, and infinitely many places V of K, or primary of primes. Let's say it in the usual language of prime. Prime P, primes of, so standard notation is OK, such that the local degrees were unramified. Let's say unramified, so that they split into product of primes, so that the local degrees corresponding to them are all divisible by P. And this has an obvious consequence. If you look at the Brouwer group of K, goes into the Brouwer group of K, the P component where P is like that, the P component of the kernel is infinite. Because you construct elements in the Brouwer group which are going to be killed by saying, I take their local invariant to be 1 over P at each of these places, some 0 I can arrange, removing that, and then I find that. Corollary, if you take K star divided, you divide by the norm, the P part of that is infinite. So you see, these are rather nice looking theorems in number fields. Also, it's an exercise to see that these things are equivalent really to the statement over finite groups. Because if I give myself a finite group and a subgroup, there is no problem in finding a capital K and little k. I will make an L with Galois group G, H will be that, and I have translated. I am not asking that K is Q. You see, I'm accepting anything, and that's very trivial. And so all those things are true, and I found them very, very beautiful. I read them in a paper in Krell around 1982. But I was not so happy with the proof, because the proof said first they use the classification. Yes, you reduce it to the case of a simple group. That's not hard. And then they said, then we have to check it for the Chevalier and so on and sporadic, and they give a proof for the Chevalier and so on. For the sporadic, they give one example, and they add the general case follows from published and unpublished properties of the sporadic groups. And that's where the situation is, you see. Okay, so you can understand that I was not so happy with that. I wanted to tell you that story because most people, when they go into mathematics, they like, that's my case, the fact that what we do is true, and that we can justify that it is true. And here we are in a really gray situation, intermediate between mathematics and physics, or geography, where you have to accept the atlas. And I cannot offer any remedy for that. That seems to be what the situation is. Thank you.
Professor, what's the status of the conjecture about all groups being Galois groups of some kind?
Not much. More and more groups are found, but the entire question is open. Yes. I don't remember. I think among the sporadic, I think there is still one which is resisting. I'm not sure. I think it's Matthew 23, but is that but even for the Chevalier groups, I mean, for a long time it was even making PSL2P as a Galois group is not a trivial matter. And if you put the power of the prime, it's no, people are finding them one by one. So, well, collections, but also I don't see any reason for this to be true. The only reason to try to prove it is that really one sees no way of counterexample it. One cannot imagine any property of a group which we could prove that it is not a Galois group over Q. On the other hand, constructing, we have many methods for constructing. So that is probably why people work in that direction.
One opportunity to think about the classification, that it's not what we quite thought it was, and that it matters. So this was.
What?
I wanted to thank you for, first of all, telling us that the classification is perhaps not quite as clear as we thought it was.
People like Aschbacher says it is proved because I think in his mind he is able to see the various species which are in the literature and see essentially that they connect. But for us, I would not consider that as a proof if there are pieces which you have to arrange. I mean, after all, many more are like that. The situation, I think, is acceptable when people say my theorem depends on the classification. I mean, that is perfectly okay. It's modulo. What is much more troublesome is that when it depends on the atlas. And that's very often the case. That really, for instance, I discuss it with the people who are writing the long redaction of the proof, and Solomon told me that they're careful not to use anything in the atlas, in the proof. They use only things which are really proved. That's the rule of the game.
So, another question?
Yes?